Welcome to DAR Tutors. Today, we will explore key concepts in vector algebra and geometry that are central to the IB mathematics, applications and interpretation higher-level curriculum. We will cover the scalar product, also known as the dot product, and the vector product, or cross product. For each, we will define the concept, develop its formula, examine its geometric properties, and work through several examples. Finally, we'll conclude with a set of IB-style practice questions to solidify your understanding. We begin with the scalar product. Our learning objective is to understand the definition and formula for the scalar product and use it to calculate the product of two vectors. The scalar product is an operation that takes two vectors and produces a single number, or a scalar. For two vectors, say vector A and vector B, their scalar product is denoted by a dot between them. This notation is why it is often called the dot product. The formula for the scalar product depends on how the vectors are represented. If the vectors are given in component form, the calculation is straightforward. For two-dimensional vectors A with components A1, A2, and B with components B1, B2, their scalar product is the sum of the products of their corresponding components. A1 times B1 plus A2 times B2. This rule extends directly to three dimensions. For three-dimensional vectors A, A1, A2, A3, and B, B1, B2, B3, the scalar product is A1, B1 plus A2, B2 plus A3, B3. In other words, you multiply the x components, multiply the y components, multiply the z components, and then add those results together. This calculation is a fundamental skill. Let's work through some examples to practice. Consider finding the scalar product of the vectors 2i plus j minus k and 2j plus k. First, it's helpful to write these in component form. I plus j minus k becomes 1, 1, 1, and 2j plus k becomes 0, 2, 1. Remember that if a component isn't explicitly written, it's 0. Now we apply the formula. We multiply the x components, 1 times 0, then the y components, 1 times 2, and finally, the z components, 1 times 1. Adding these gives 0 plus 2 minus 1, which equals 1. The result is a scalar, as expected. Let's try another one with three-dimensional vectors. Let's find the scalar product of the vector A equals 3, 1, 2, and the vector B equal 1, 1, 1. Using the component formula, we have 3 times 1 plus 1 times 1 plus 2 times 1. This simplifies to 3 plus 1 plus 2, which equals 0. A result of 0 has a very important geometric meaning, which we will discuss next. In this scene, we have defined the scalar product and demonstrated how to calculate it using component vectors, thus meeting our objective. In this scene, our goal is to derive the alternative geometric formula for the scalar product and use it to find the angle between two vectors. The scalar product can also be defined in terms of the magnitudes of the vectors and the angle between them. Let's see how this formula is derived. Consider two vectors, vector A and vector B, that originate from the same point. If we draw a third vector, B minus A, connecting their endpoints, we form a triangle. We will call the angle between A and B theta. In any triangle, the law of cosines relates the lengths of the sides and an angle. Applying it to this vector triangle, the square of the magnitude of B minus A is equal to the sum of the squares of the magnitudes of A and B, minus 2 times the product of their magnitudes and the cosine of the angle theta. So B minus A squared equals A squared plus BA squared minus 2A tab cos theta. Now let's substitute the component forms of the vectors into this equation. This part can be a bit long, so let's simplify the process by working with the scalar product in the algebraic definition. Let's expand the left side of our equation in terms of the scalar product. B minus A tan shi a squared is the scalar product of B minus A with itself. Using the distributive property of the scalar product, we can expand this. This gives us B dot B minus A dot B minus B dot A plus A dot A. Since the scalar product is commutative, B dot A is the same as A dot B. Also, the dot product of a vector with itself is the square of its magnitude. So our expanded form simplifies to tish BEA squared minus 2 A dot B plus A gichi out A squared. This is a much cleaner way to represent the left side. Now let's equate this with the law of cosines equation we had earlier. We set back up a ba squared minus 2 a dot b plus a squared equal to ca squared plus ba squared minus 2ab by a cos theta. We can see that ca squared and ba squared appear on both sides of the equation, so they cancel out. This leaves us with quash 2 a dot b equals 2 quad to a b ska al theta. Dividing both sides by y2 gives us the fundamental geometric formula for the scalar product. A dot b equals the product of the magnitudes of a and b times the cosine of the angle between them. This formula is crucial for understanding the geometric significance of the scalar product. A direct consequence is a formula to find the angle between two vectors. By rearranging the equation, we find that the cosine of the angle theta is the scalar product of the vectors divided by the product of their magnitudes. The angle theta is defined to be between 0 and 180 degrees inclusive. Let's apply this formula. Suppose we have vectors p equal 2, 3, so 1, and q is so 1, 0, 2. Let's find the angle theta between them. First, we calculate their scalar product, 2 times a 1 plus 3 times the 0 plus 1 times 2, which gives 2 plus 0 minus 2, or 4. Next, we find their magnitudes. The magnitude of p is the square root of 4 plus 9 plus 1, which is the square root of 14. The magnitude of q is the square root of 1 plus 0 plus 4, which is the square root of 5. Now we plug these values into the angle formula. Cos theta equals 4 over the square root of 14 times the square root of 5, which is 4 over the square root of 70. To find theta, we take the inverse cosine. Theta equals arccos of 470, which is approximately 118.6 degrees. Notice that because the cosine is negative, the angle is obtuse. This aligns with our formula and gives us a clear geometric interpretation. We will now examine the geometric properties of the scalar product. Specifically, our objective is to use the scalar product to determine if vectors are perpendicular or parallel. The geometric formula a dot b equals clash a ba is. Theta provides two powerful tests for the relationship between two non-zero vectors. First, for perpendicular vectors. If vector A is perpendicular to vector B, the angle theta between them is 90 degrees. Since cos 90 degrees is 0, 0, the entire expression becomes 0. Therefore, if two non-zero vectors are perpendicular, their scalar product is 0. The reverse is also true. If their scalar product is 0, they are perpendicular. This gives us a simple and powerful condition. A dot b equals 0 if and only if a and b are perpendicular. Second, let's consider parallel vectors. If vector A is parallel to vector B, the angle theta between them is either 0 degrees, same direction, or 180 degrees, opposite directions. If theta is 0 degrees, cos 0 is 1. If theta is 180 degrees, cos 1 is 1. In either case, the value of the scalar product is plus or minus the product of their magnitudes. This means that the absolute value of the scalar product is equal to the product of the magnitudes. If this condition holds, and the vectors are non-zero, they must be parallel. So we can test for parallel vectors by checking if this equality holds. Let's use the perpendicularity test. We are asked to show that the vectors v equals 1, 1, 5 and w equals 2, 3, 1 are perpendicular. The condition for perpendicularity is that their scalar product must be 0. Let's calculate it. The scalar product v dot w is 1 times 2 plus 1 times 3 plus 5 times 1. This is 2 plus 3 minus 5, which equals 0. Since their scalar product is 0, we have successfully shown that the vectors are perpendicular. This confirms their orthogonality. Now, let's look at a problem that requires us to work backwards. We'll use the perpendicularity condition to find an unknown component. We need to find a scalar t such that the vector p et 3t and the vector qe, or 2, 1, are perpendicular. Again, if they are perpendicular, their scalar product must be 0. We set the scalar product p dot q equal to 0. This gives us 3 times 2 plus t times 1 equals 0. Simplifying, we get 6 plus t equals 0. Solving for t, we find that t must be 6. Therefore, the value of the component t is 6 for these vectors to be perpendicular. In this scene, we have established the conditions for perpendicular and parallel vectors using the scalar product and applied these conditions to solve problems. This concludes our objective. Our objective now is to find all vectors perpendicular to two given non-parallel vectors. This will lead us directly to the vector cross product. Let's consider two non-parallel three-dimensional vectors, vector A and vector B. We want to find a new vector. Let's call it vector x, that is perpendicular to both A and B. If vector x is perpendicular to A, their dot product must be 0. Similarly, if x is perpendicular to B, their dot product must also be 0. Let vector A have components, 1, A2, A3, vector B have components, B1, B2, B3, and vector x have components, x, y, z. The conditions for perpendicularity give us a system of two linear equations. The dot product condition gives us the first equation, a1x plus a2y plus a3z equals 0. The second dot product condition gives the second equation, b1x plus b2y plus b3z equals 0. We have two equations and three unknowns. This type of system usually has infinitely many solutions. Let's solve it for x and y in terms of z. Rearranging gives us two equations in x and y that depend on z. We can eliminate x using a standard method of multiplying the first equation by negative b1 and the second by a1, and then adding them. The x terms cancel, and after some algebra, we can solve for y in terms of z. By a similar process of eliminating y, we could also solve for x in terms of z. The result of this lengthy algebraic derivation is the following. A solution vector x has components that are specific combinations of the components of a and b, all multiplied by some scalar t. This scalar t can be any non-zero real number. The direction is fixed, but the length can vary. This specific direction vector has a special name and notation. When we let the scalar t be 1, we get the vector across b. This is the vector product of a and b. It results in a vector that is perpendicular to both a and b. It is only defined for three-dimensional vectors. Memorizing this formula can be cumbersome. Fortunately, there's a much more intuitive way to calculate it, which we'll explore next. In this scene, our objective is to learn and apply the determinant method for calculating the vector cross product, which is simpler and less error-prone than the component formula. The formula for the vector cross product can be written using a determinant, which is a value associated with a square matrix. You've likely seen 2x2 determinants before. The determinant of a 2x2 matrix is the product of the diagonal elements minus the product of the off-diagonal elements. For the cross product of three-dimensional vectors, we'll use a special 3x3 determinant. The first row consists of the standard unit vectors I, j, and k. The second row contains the components of the first vector, A. The third row contains the components of the second vector, B. So across B equals the determinant of the matrix with rows I, j, k, a1, a2, a3, and b1, b2, b3. To calculate this, we use a method called cofactor expansion along the first row. This may look complicated, but there's a simple pattern. The result is I times a 2x2 determinant minus j times another 2x2 determinant plus k times a third 2x2 determinant. Notice the minus sign on the middle term. It's a common mistake to forget this. This is a crucial detail for the sign to be correct. To find each 2x2 determinant, you cover the row and column of the unit vector you're multiplying by. Let's practice with an example. We'll find the cross product of A equals 1, 2, 3, and B equals 1, 3, 1 from our earlier exercise. First, we set up the determinant with ijk in the top row, the components of A in the second row, and the components of B in the third row. Now we expand. For the I component, we cover its column and row. The determinant is of the remaining matrix, 2, 3, over 3, 1. For the j component, we cover its column and row, taking the negative of the determinant of 1, 3 over to 1, 1. For the k component, we cover its column and row, taking the determinant of 1, 2 over to 1, 3. Let's calculate each 2x2 determinant. The first is 2 sur 1, 3 to 3, equals to 2, 9 equals 11. The second is 1 or 1, 3, 1, equals to 1, 3 2. And the third is 1, 3, 2 sur 1 e 3 2 5. Putting it all together, we get 11i minus 2j plus 5k. In component form, this is post 11 or 2, 5. This vector is perpendicular to both A and B. We have now successfully calculated a cross product using the determinant method, achieving our objective. This method is much more reliable once you get comfortable with the pattern. Pause for a moment. This has been a lot of information. We've just reached a natural breakpoint. If you're finding this content helpful, you might consider reaching out to DAR tutors for personalized expert tuition in IB, A-Level, and IGCSE curricula. Our experienced tutors can provide the in-depth support you need to master these concepts and excel in your exams. Our objective for this section is to explore the algebraic properties of the vector cross product, which will give us a deeper understanding of how it behaves. The vector cross product, unlike the scalar product, has some unique algebraic properties that are important to know. These properties can simplify calculations and provide deeper insights. First, the cross product of any vector with itself is the zero vector. Let's prove this quickly. If A equals B, then across A will have identical rows in its determinant. A property of determinants is that if two rows are identical, the determinant is 0. So, across A is the zero vector. Second, and this is a very important one, the cross product is not commutative. In fact, it's anti-commutative. This means that across B is equal to the negative of B cross A. The vectors have the same magnitude, but point in the exact opposite direction. This happens because swapping the second and third rows of the determinant changes its sign. Third, the cross product is distributive over vector addition. This means across the sum of B and C is the same as across B plus across C. This is a very useful property when dealing with sums of vectors. It works just like regular multiplication over addition. A related concept is the scalar triple product, a dot B cross C. This takes 3 vectors and produces a scalar result. We can calculate this in 2 steps. First, find the vector B cross C. Then take its scalar product with A. Alternatively, the scalar triple product is given by the 3×3 determinant of the 3 vectors. This result has a significant geometric meaning that we will explore later. Let's work through an example of the scalar triple product to see how the properties can be applied. Consider the expression a dot, B cross CC. We know B cross C is a vector perpendicular to both B and C. So if we take the dot product of A with this resulting vector, we are finding how much of a lies in the direction perpendicular to both B and C. Intuitively, across B is perpendicular to A. Therefore, the dot product of A with a vector that is perpendicular to it should be 0. Let's prove it algebraically. The scalar triple product is the determinant of A, and B. Since 2 rows are identical, the determinant is 0. So a dot across B is always the scalar 0. This makes sense geometrically. A similar result is true for the other vector, B dot, across B, is also 0. So we've seen how a few key algebraic properties of the cross product allow for quick proofs and a deeper geometric understanding, which completes our objective for this scene. We have established that the vector across B is perpendicular to both A and B, but which of the 2 possible directions does it point? In this scene, we will learn how to determine this direction using the right-hand rule. For any 2 non-parallel vectors A and B, there are 2 vectors perpendicular to both, one pointing in a specific direction and its negative pointing in the opposite direction. The direction of across B is determined by the right-hand rule. Here's how it works. Using your right hand, point your fingers in the direction of the first vector, A, then curl your fingers towards the direction of the second vector, B. Your thumb will now be pointing in the direction of the cross product, across B. This rule gives a consistent way to determine the direction. Now, let's look at the length, or magnitude, of the cross product. Our next objective is to derive the geometric formula for the magnitude of the cross product, which connects it to the sine of the angle between the vectors. We have 2 ways to calculate the magnitude of the cross product. The first is by calculating the vector across B using the determinant method, and then finding its magnitude as usual. This involves a potentially long calculation. The second geometric formula is much more elegant. The magnitude of across B equals the magnitude of A times the magnitude of B times the sine of the angle theta between them. Let's quickly see how this is proven. It comes from an identity involving the scalar and vector products. We know the scalar product is related to cos theta and the cross product to sin theta. A key trigonometric identity is sin squared plus cos squared equals 1. This connects the geometric formulas. Multiplying by a squared, b squared gives us this expression. Substituting the geometric definitions of dot and cross products gives us a cross bo squared equals the a squared, ba squared minus dot b squared. While expanding the algebraic forms of the dot and cross product squares and simplifying is a very long process, it will eventually lead to this exact identity. And by taking the square root, we confirm the geometric formula for the magnitude. This formula gives us an immediate consequence. If the cross product of two non-zero vectors is the zero vector, then the angle theta must be 0 or 180 degrees. This means the vectors are parallel. So, across B equals the zero vector if and only if A and B are parallel. This provides another powerful test for parallelism, especially in 3 dimensions where the component method is less direct. We have now covered both the direction and magnitude of the vector cross product, which were our objectives for this scene. We now turn to a powerful application of the cross product, calculating areas. Our objective is to learn how to find the area of a triangle or a parallelogram using the vector cross product. The magnitude of the vector cross product has a direct and beautiful geometric interpretation as an area. Consider a parallelogram defined by 2 adjacent vectors, A and B. We know the area of a parallelogram is its base times its perpendicular height. Let the base be the length of vector B, OSBA. The height is the magnitude of a times the sine of the included angle, A sin theta. Notice that base times height is exactly the formula for the magnitude of the cross product. So, the area of a parallelogram defined by vectors A and B is simply the magnitude of a cross B. Now for a triangle. Any parallelogram can be divided into 2 congruent triangles. This means that the area of a triangle defined by vectors A and B is exactly half the area of the parallelogram. This is a remarkably efficient way to find the area of a triangle or parallelogram in 3D space, given the coordinates of its vertices. You just form the vectors for the sides, calculate their cross product, and find its magnitude. Let's work through an example, finding the area of a triangle in 3D. First, we need to form 2 vectors that define 2 sides of the triangle, sharing a common vertex. Let's use vertex A. We'll find the position vectors of the sides AB and AC. Vector AB is the position vector of B minus that of A, giving 1, 1, 0. Vector AC is C minus A, giving 0, 1, 1. These are our vectors A and B for the area formula. Next, we calculate their cross product. Setting up the determinant, we expand it. This gives I times 1 times 1 minus 0 times 1, minus j times 1 times 1 minus 0 times 0, plus k times 1 times 1 minus 1 times 0. The resulting vector is I plus j minus k. Now we need to find its magnitude. The magnitude is the square root of 3. Finally, we apply the triangle area formula. The area of the triangle is 1/2 of the square root of 3 square units. So, we have successfully used the cross product to find the area of a triangle, meeting our objective. This method is incredibly versatile for geometric problems. We will now explore another important application, finding the component of a vector in a specific direction. Our objective is to calculate and understand the component of a vector parallel and perpendicular to another vector. Imagine a force vector F and a displacement vector D. The work done is the part of the force that acts in the direction of the displacement. This is a classic component problem. More generally, for any 2 vectors A and B, we can ask for the component of A in the direction of B. This is the length of the projection of vector A onto the line containing vector B. From trigonometry, this length is simply the magnitude of a times the cosine of the angle theta between A and B. Using the scalar product formula, a dot B equals theta shata sa B E as istat at the theta. We can solve for h SOE theta. We find that HEQ's theta is equal to a dot B divided by the magnitude of B. This is a convenient formula. Importantly, this component is a scalar. It can be positive if the angle is acute, or negative if the angle is obtuse. Next, let's find the component perpendicular to B. This is the magnitude of the other side of the right-angled triangle formed by the projection. Using the sine function, this component is clashant asenki amiki to theta. From our cross-product formula, we know neta cross BA equals A I ASCII. So, rearranging, we find the perpendicular component is the magnitude of a cross B, divided by the magnitude of B. Notice this result is always non-negative because it's a magnitude. Let's apply these two formulas with an example. First, the component in the direction of B. We calculate a dot B, which is 13. We calculate the magnitude of B, which is the square root of 35. So the parallel component is 13 over the square root of 35. Now, the component perpendicular to B. First, we must calculate the cross product A cross B using the determinant method. This gives us the vector 2, 1, 1. Next, we find the magnitude of this cross product, which is the square root of 6. Dividing by the magnitude of B, we get the final perpendicular component, the square root of 6 divided by the square root of 35. In this scene, we have derived and applied the formulas for the parallel and perpendicular components of one vector with respect to another, fulfilling our objective. Our final learning objective is to apply the scalar triple product to find the volume of a three-dimensional solid. This solid is a parallelepiped. A parallelepiped is a three-dimensional figure formed by 6 parallelograms. It's essentially a tilted box. The volume of a parallelepiped defined by 3 vectors, A, B, and C, can be found using the scalar triple product. The proof comes from the standard formula for the volume of a solid base area times perpendicular height. As we saw before, the area of the base, defined by vectors B and C, is B cross C. The perpendicular height is the component of the third vector, A, that is perpendicular to the base. This component can be found using the scalar product. Combining these, we get the volume as the absolute value of the scalar triple product, a dot B cross C. Let's apply this formula. To find the volume, we calculate the scalar triple product and then take its absolute value. Find the volume of the parallelepiped defined by vectors A equals 1, 3, 2, B equals 2, 1, 1, and C equals 0, 1, 2. The formula for the scalar triple product is the determinant of the 3x3 matrix whose rows are the components of the 3 vectors. Let's expand this determinant. We'll use the cofactor expansion along the first row. This gives us a times the determinant of 1, 1 over 1 to 2 minus 3 times the determinant of 2, 1 over 0, 2 plus 2 times the determinant of 2, 1 over 0, 1. Simplifying the expressions inside the absolute value, we get 1 times 1 minus 3 times 4 plus 2 times 2. This is 1 plus 12 plus 4, which equals 17. The volume of the parallelepiped is 17 cubic units. This method provides a powerful, concise, and direct way to calculate the volume of a parallelepiped. It is also an important result to use for checking if 3 vectors lie in the same plane, which is called coplanarity. If 3 vectors are coplanar, they cannot form a three-dimensional solid, so their scalar triple product will be 0. We have now achieved our final objective for this topic. We will now work through 5 IB-style practice questions that test the concepts we've learned. Question 1 asks for the scalar product of 2 vectors given in component form. You should attempt to solve this before watching the solution. Solution 1. We use the component formula for the scalar product. We multiply the corresponding components and add the results. 1 times 3 is 3. 2 times 1 is 2. 1 times 4 is 4. The sum is 3 minus 2 minus 4, which equals 3. The scalar product is 3. Question 2 asks for the value of a scalar k given that 2 vectors are perpendicular. Solution 2. Recall that 2 non-zero vectors are perpendicular if and only if their scalar product is 0. We set the dot product of p and q to 0. This gives us the equation 3 times 1 plus k times 2 plus 2 times 4 equals 0. Simplifying, we get 3 plus 2k minus 8 equals 0. This simplifies to 2k minus 11 equals 0. Solving for k, we find k equals 11 over 2. The value of k that makes the vectors perpendicular is 5.5. Question 3 asks us to find the area of a parallelogram defined by two vectors. Solution 3. The area of a parallelogram is the magnitude of the cross product of its defining vectors. We will use the determinant method to calculate u cross v. Setting up and expanding the determinant, we get I times 2 minus 3, minus j times 4 minus 12, plus k times 2 plus 4. This simplifies to I plus 16j plus 6k, or the vector 1, 16, 6. Now we find the magnitude of this vector. The magnitude is the square root of 1 plus 256 plus 36, which is the square root of 293. The area of the parallelogram is the square root of 293 square units. Suppose. Question 4 involves finding a unit vector perpendicular to two given vectors. Solution 4. We know that the cross product across B gives us a vector perpendicular to both A and B. A unit vector in that direction is found by dividing the cross product by its own magnitude. First, we calculate the cross product. The determinant expansion gives us I times 1 minus j times 1 plus k times 1. So, across B is the vector 1, 1, 1. The magnitude of this cross product is the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3. Finally, we divide the cross product vector by its magnitude to get the unit vector. The unit vector perpendicular to both A and B is 1 over the square root of 3 times the vector 1, 1, 1. Our final question asks for the volume of a parallelepiped using its vertex coordinates. Solution 5. The volume is the absolute value of the scalar triple product of the three defining vectors, which are the position vectors of the vertices P, Q, and R. We calculate the scalar triple product of vectors OP, OQ, and OR. Expanding the determinant, we get 1 times 12 minus 2 minus 1 times 8 minus 3 plus 0. This simplifies to 1 times 10 minus 1 times 5. The result is 10 minus 5, which equals 5. The volume of the parallelepiped is 5 cubic units. In this section, we have applied our knowledge of the scalar and vector products to solve typical IB-style problems, covering a range of topics including calculating products, finding angles, determining perpendicularity, and calculating areas and volumes.